Hello, how y'all doing today? My name is Bernie Thompson, and today we're here to take a look at this 2017 Subaru WRX. These little WRXs, they're some fast running cars. So if the car doesn't perform right, the driver will know it right away. And this vehicle supposedly has a low power problem, but it's intermittent. It mainly happens when the vehicle gets hot. The car's been to several shops trying to be repaired. They've put a turbo on it and a bunch of other components. Now our job is to properly diagnose this car to figure out what's wrong with it. So the first thing I want to do is I want to put a scan tool on it and go drive it around and get some basic data so we can figure out what to do with this vehicle.
Marginal.
Okay guys, I got the scan tool up. I've been driving the car to get it warm. I've got my data. I'm centered and I've got stoichiometry, so this is a wide RAF sensor. I've got a real light fuel trim, both short and long. It's light, it's yellow, so it's not a heavy trim, and we're at idle. And this car has a low power under full load.
Fuel trim.
The time to engine temperature is good. I'm at 204, and I've been driving it, so it's hot. They said it only does this when it's hot. I've got good vacuum, charging is good, I have no DTCs, and my monitors, I have 3 that haven't been run, but we already know they've been clearing the codes. They've been trying to work on this car. First thing I want to do is come over here, and I want to go ahead and I want to run a fuel trim test. So we're going to just start rolling, and then we're going to get into the gas a little bit. So I'm in the throttle hard, and it ran good, and we pulled up towards 18 psi on the gauge. The car is definitely pulling fine right now. There's no problem with the way this car pulls. So I want to do one other test now. The fuel trims all are fine. I don't see any kind of a fuel trim issue. So now what I need to do is I need to run a volumetric efficiency test. That's how much air this engine can pump. So we're going to go ahead and go over to VE and go here, and this is a turbocharged car, so sometimes the VE doesn't match exactly right, but I'll show you how to deal with that. So we're going to go ahead and we start rolling, and we're going to go ahead and floor it in first. Car pulled good. The turbo's coming up to about 18 pounds of boost, so that's good. So let's look at this data real quick so we can see it. Okay, so the VE came up, and basically we're pulling about 180 grams per second under full boost, 180 grams per second. Now to check how much that is, we're going to come do the power test. Now this is a horsepower calculation based off of how much air it pumped. Since this is a turbocharged car, I'm not sure that the VE is right, although it does say it's scaled, so we've scaled this car. But an easy way to do this is the rated horsepower is 268, and basically we're making 240 horsepower, and that's a mile high. So basically I'm okay on my horsepower. I don't seem to have a problem right now. So this is doing well. I've got enough horsepower, and we've pulled our load, and we've got about the right gram weight of air. So the gram weight of air, right now the car's running good, and we got about 180 grams when it runs good, and we know we're pushing about 18 pounds of boost by the gauge. Now that we know these things here are correct, what I want to do now is I want to go over to the PIDs, and I want to drive the car and try to get it to mess up, but I want to get a couple of other things. So this has got a RAF sensor, so the first thing I want to do is I want to get the lambda from the RAF. What is the lambda doing? Okay guys, I've changed some of the data I'm collecting on the scan tool. Let me go over this. So I've got the RAF sensor's lambda right here. So this should be a lambda 1 at idle, which it is, and under load we should go to about 0.9 or 10% rich. This guy right here is the map, and this pressure, under pressure, this has got good vacuum right now at 22 kPa. My atmosphere is 83 kPa. So I would assume that this is going to hit somewhere around 180 or 190 kPa, which is going to be about 18 pounds of boost.
Correction, good.
The gram weight of air, we already know it should be about 180 when it's under full pull. And this is my theoretical airflow, so this is what we looked at with the VE table. These are being compared against each other. This is total trim. I'm taking away 6% right now. And this is my throttle position. So let's go ahead and see what we're going to get for a pull. It's starting to get warm, so maybe we'll see it. Okay, so we're going to get in it. It's laying down. It's not pulling good at all. We're at 0.8, 0.78. Now it's pulling good. So it started out there to not pull very well. I feel what the shop is talking about right there. So we're in a lean cut. We're 50% lean right now. I'm in it. 0.73, and it's not pulling good. So this thing is so rich, it doesn't pull good. We've got pressure, so we're making pressure, and the volumetric efficiency is also there. So we've got the right VE and we've got the right pressure, but we're way too rich. Okay, so let me just think about this. Okay guys, so what I'm seeing is when it laid down, it's too rich. It's 30% too rich when it wants to lay down. And then when it started to pull, it came back up and it was about 10 or 15% too rich. Now, I'm not sure, but with a turbo, 30% might bog me, but I don't think so. Usually if it's rich, the turbo will spin better and I'll get good boost, but it was bogging it when it laid down. I could feel it. But the pressure came up and the VE was there, so those things seem to be right, but the fuel is too much fuel. Now, either I have too much fuel or I don't got enough air. Now, if the mass air was reading it like we saw, the VE read it right, but I have a leak, like after the turbo, it would pull the air and then it could bleed out on the high side pressure, and that might give me the right VE and I would be rich, but I don't think I would still have the same pressure.
One fuel trip.
In other words, if I've got, you know, 200 kPa, 20 psi, if I had a leak big enough down low before the turbo spun up, I still don't think that I could hit that boost and it would be that good. So I'm not thinking that this is a boost leak. What I'm thinking this problem is something to do with the RAF sensor is misreading the air. So the first thing I want to do here is I want to go get a gas analyzer, and I want to get a gas analyzer and read the tailpipe exhaust against this RAF sensor. I want to confirm it because that's the easiest test I've got to do right now. Because the only things I really can think that would make that car lay down like that is it's really lean, but the thing is saying it's rich, because that's almost what it felt like. It felt like it laid down and then it pulled once it, like the fuel, something with the sensor started to read more correct and it started to pull better. So I think my problem is with the RAF sensor right now, but it could be if I had a leak and it might leak some and then the turbo overcomes the leak and I have full pressure. I just don't think I could make 20 pounds if I had a leak big enough to lay the car down like that. So the first thing I want to do, I want to confirm the air fuel. So let's go get the gas analyzer and get that installed on this vehicle and test it while it's doing it. Okay, let's go ahead and get that gas analyzer so we can get that on the car and go drive it. This is the brand new gas analyzer by ATS. This gas analyzer has a lithium-ion battery that's quickly changed and charged. This has a very large pump in it, which limits the latency between the tailpipe, pulling it out of the tailpipe and reading it to the sample cell. This also has a really unique 2 sample cells. So there's 2 IR sample cells in this machine. One is very small and one is very large. The very small one gives us very, very fine accuracy with just a few parts per million. And the large cell gives us accuracy with a lot of gases. So we can read very low gas traces far more accurately now than we could before. We also have less latency. This just flat out is the next level of gas analyzers. Let's go ahead and get this in this car and go for a test drive. Okay guys, I got the gas analyzer up. Let me show you what we got. These are the gases right here. 8C, NOx, CO, lambda, CO2, and the O2. The air-fuel ratio is given right here. Now this right here is the lambda from the gas analyzer, and this number right here is coming from the scan tool. I've opened up the multi-tool and I've picked the lambda from the scan tool, the lambda from the gas analyzer. That's what I can pick which ones I want to put here. And then I got total trim over here, and I've got the map pressure in blue. So that's the way the screen is set up. The only thing I'm really worried about right now are these two. Now right now they're both 1 and 1, and I'm sitting here at an idle. I'll give it some RPM. Now they're 1 and 1. They're matching each other, so that's what should happen. I expect these to be right on top of each other. So now let's get a little load on this car.
Good.
Let me get my seatbelt on here. Okay, and again, these are mirroring each other, as you can see. What's coming out the tailpipe, it's what's being read by an O2 or a wide range. They've got to be the same. If they're not, there's something wrong with it. We're going to drive up here where I can get this car under load. Being it's a turbo car, we don't want to be turboing in a neighborhood like this. I want to be on a bigger road like we were on. So let's go back up here. I drove the car around quite a bit prior to starting to film this so I could get it hot where we could maybe get it to fail. The shop told me I had to drive it for about a half an hour before it was going to fail. So this is a pretty good shop I'm doing this for. They actually pay attention to things and give me some detail about what I'm looking for. So it saves me quite a bit of time once I'm actually looking at a car. So again, we're 1 and 1, 1 and 1. These are following each other. This is from the scan tool. This is from the gas analyzer. We're really close on those numbers, so we're really close. We're staying right on.
Good.
So that's okay, and that would tell me if we get under boost when we have the problem and they match each other, then that tells me the mixture is really rich, and then that's going to take me in another direction. If they don't match each other, then it's a problem with the feedback circuit, and then I'm going to need to look at that. Right now, I'm just trying to figure out where I'm going to go. What am I going to do to fix this car? It laid down right there, and I went way rich, and the gas analyzer did not match. So we're going to get in it. 0.79 and 1. 0.73. Okay, what's coming out the tailpipe does not match the RAF sensor. So the RAF sensor has drifted its calibration, and it only happens when it gets really hot after it's been driven a while and under load. As we can see, when I was just cruising along, they match each other pretty well, but the car doesn't have a problem then. The car's having a problem when I get this car under a loaded condition. So let's watch this again.
Bank 1 fuel trip.
I'm going to get in it. It pulled okay that time. I could feel it sort of lay down at the beginning. Let's get in it again. It's laying down, it started to pull. Those two aren't close. I'm at 0.98 and I'm at 0.7. I'm 30% difference in my fuel delivery or my fuel call out there. This is a problem. Okay guys, what we got to do now is I need to go get my scope leads and I need to get into this RAF sensor, wide range air fuel sensor, so we can see what's going on, because the RAF is not matching what's coming out the tailpipe. Now that's a problem. They got to be the same. They got to match. Like right here, you can see when I'm cruising along, they're at least fairly close. Okay guys, I've got the scope connected. No, this RAF sensor is a little bit different than I'm used to. On most of the Subarus that I've looked at, they have a RAF sensor and it's a 6-wire RAF. It's a Bosch unit, and the 6-wire goes to a calibration resistor that's in the connector. Now this is a 5-wire LAF unit. Now these operate a little bit differently because they don't have the calibration circuit, but basically they're the same. They have 2 oxygen sensors. One reads, one's a sensing cell and one is a pumping cell that's pumping oxygen in and out of a diffusion chamber. Bosch put a resistor to calibrate that diffusion sensor size, but the LAF sensors don't do that. They just use the oxygen to pump in and out, and it's accurate enough, they say. A lot of that has to do with patents, and Bosch has patents, so to not infringe, you start to see other designs, such as a 5-wire LAF rather than a 6-wire RAF. They're a little bit different. They both use 2 sensors and they both use a pumping cell. So we're going to have a sensing cell voltage and we're going to have a pumping cell voltage, and that pumping cell is going to be going up and down across that sensing cell. Now the other thing that we have is on these sensors, it is super important to keep it hot. That means the heater has to work. Now in the early LAF sensors where there's 2 bulbs, like on Hondas, that's what I'm really familiar with when I see a 5-wire, is Honda's early ones. It takes 5 amps or so to keep it hot. Now anything this new in a 17 is going to be plain air. That's where the heater is embedded in the sensor itself, so it will take far less current. I'd expect it takes about an amp on this particular circuit. Let's take a look at where we've hooked up here. So here's the sensor, and I've got my 5 leads and I've got my amp clamp. And it's super important to realize that these sensors, they have to have heat to make them work. An oxygen sensor, they only have to be about 700 degrees to work. A RAF's going to need to be 1600 to 1700 degrees to work. Now 700 degrees, I can get the sensor that hot on the gasoline just burning. But 1700, that's way hotter than the gasoline is going to be able to heat this to. So you have to have a heating element. So it's going to be really important, especially on a system that's out of range, to make sure that that heater is working properly, because if the heater didn't have enough current, it would skew the reading. So let's go ahead and go for a test drive. Let's go drive this car and see where we're at now. Okay guys, I got the scope connected. Let me show you what I got. Okay, so the red trace is the sensing cell and the green trace is the pumping cell. When the pumping cell goes above the sensing cell, it's lean. When it drops below the sensing cell, it's rich. What it should really do is it should just bounce up and down. And if it's bouncing up and down, that's what I expect it to do, and that shows me that I'm calibration, or not calibration, but a lambda of 1. This is my heater, and down here in purple, my heater is pulling 1 amp. So the heater is okay. That's about what I'd expect. Over here, this is my multi-tool. This is the lambda from the scan tool. This is the LAF sensor itself, a lambda of 1. This is my exhaust gas analyzers, a lambda of 1. This is my total trim for bank 1. This is my map. So 20 kPa, I've got a pretty good vacuum going right now, but when we start to boost, this will come up close to 200. So that's what we've got laid out. Now, if the green trace goes way low and stays low, and the LAF says I'm rich, and my gas analyzer says I'm not rich, well then I have a calibration failure in the LAF sensor. And that can happen for a couple of reasons that we'll go over here in a little bit. That's either the sensor could be cracked and exhaust gas can get into the cell chamber, or the oxygen is restricted and when I don't have enough oxygen to pump in and out of the chamber. Remember, these are dual cells chambers. There's 2 oxygen sensors inside here. So now is what I want to do is I want to go ahead and we want to pull out and see what this is going to do. So we're going to just drive along. And so this is bouncing. That shows I've got control. I'm a lambda 1, a lambda 1. I'm going to get in it. It didn't really lay down that time very good. Okay, it didn't pull that bad there. It's not doing as bad as it was earlier. And this is an intermittent problem, so let's go back down into second because that's where I felt it the best. So we're going to get in it. It's laying down. I went all the way to 7.3 and I'm lean on the gas analyzer. So I was almost at 1.3, 1.4, 40% lean. That's when it laid down, and this is telling me I'm rich. That RAF is flat out of calibration, and the sensing cell was rich. It stayed down below when that happened. So that tells me that the RAF is out of calibration. The RAF's calibration is drifted, and now that's going to give me a problem in the control of the car and the fuel system. And just for you guys that have never programmed any control systems, a slight fuel change in the control of a car makes a huge change in how it feels like it's pulling. When I was calibrating race engines, we would go drive them in the desert. I was race desert cars, and I'd make a slight fuel change to the command with my computer connected, and you could really feel it. Sort of like this, it's just laying down. But right there, we were actually lean. We were lean on the tailpipe exhaust, and the exhaust from the RAF says it's way rich.
Correction.
Now that's just flat wrong. So the RAF is definitely out of calibration. And we got to fix the fuel before we can do anything else. If the car has another problem, step 1 is to fix this fuel. The fuel has to be matched. Those 2 sensors have to match each other before we can move on to see what else might be wrong or if this is just what's wrong. So we need to take this back to the shop, and we need to get them to replace that sensor, and then we'll come back and we'll get this tested, guys. Okay guys, we're back over at the shop, and they've replaced the RAF sensor, the wide range air fuel sensor, in this little WRX. I've got my scope on it, I've got my gas analyzer, and I got a scan tool on it. I just got it installed. So now let's go for a test drive and see how this car does. Okay guys, I got the scope connected to the RAF sensor. This is the scan tool, and this is the lambda from the sensor. This is the tailpipe lambda. This is my total trim, and this is my map pressure. Let's go ahead and fire this beast up and see what we've got. Okay, oh wow. We have way more current, guys. We have 2.8, almost 3 amps of current. Before we only had 1 amp. Now I'm not real familiar with these 5-wire RAFs in these Subarus, but apparently they need 3 amps, not 1 amp. Now that could be our whole problem, because when you have a lot of this, where we had a problem or a calibration issue was under full load. Now under full load, you have a lot of air going out the exhaust. Now that air will cool that sensor down. Air is a really good conductor of heat, so that's like why you can go fully rich under wide open throttle and you don't damage your cat. You can be rich, but you have so much airflow under wide open that air is cooling the cat where it doesn't become damaged. Now under full load, If we cool that sensor down, it's going to lose its calibration for sure. Now I know that this sensor needs 3 amps, not 1 amp. Well, that, if I'd have seen that, I'd have known right away what was wrong. So we had to go a long way around to make sure that sensor was bad. But now I know the sensor had a problem. There's a huge difference between 1 amps and 3 amps in the amount of heating capability that can give that sensor. So let's go ahead and drive this thing. Let's take it for a test drive and see what it's going to do. Okay, we're on our test drive, so let's go ahead and see what this thing's going to do now. So the sensor might be a little bit more active now. We can see the pumping cell is moving up and down by the sensing cell. The lambda is exactly the same. Let me change this real quick so we can see the lambda a little better. So now these are the lambda. This is from the RAF sensor. This is from the gas sensor. Really close on the two, as we can see. They're both reading very close, and that's what we should see. Now, we had that before until we got under load. Up here, when we get on a different road, I'll be able to put this under load, but right now let's just cruise and see what it does. So they're staying right on. So the tailpipe is reading the same thing as the RAF, and that is what I expect this car to do. So they're reading really close. I'm going to get it under load. It's pulling. The boost is up. We're at 16, 18 pounds boost. We're really close now. Look at that, guys. Do you see how that's reading the same? We're about 18% rich. I'm going to cut. I'm going to get out of it. So we're going to get into a lean cut now. Okay, that's great, man. That's what should happen. The two have to meet each other. So the tailpipe has to be reading the same thing as the RAF. When you don't have that, you have some type of a feedback problem, as we've seen on this car now. Okay, guys, this is the scope with the gas traces. Okay, they're even. Let's go ahead and get in it. We're under boost. 18 pounds of boost right there. You can see what the trace is going to do from the sensor. I'm going to get out of it. That's a lean cut right there. So we can see that that current is quite different than it was prior to putting the sensor in this vehicle. Okay guys, we're right off of our test drive with this little Subaru WRX. And as we can see, this RAF sensor is now reading the correct air-fuel ratio from the fuel mixture. Now this can be a really tricky problem to diagnose. This is not an easy diagnostic problem. How do you diagnose a car with no fuel trims and no DTCs? It becomes a challenge. Now, The only way I really know how to check the calibration of an oxygen sensor or RAF sensor is with a 5-gas analyzer. With gas analyzation, you can actually tell what the gases coming out the tailpipe are, and you can compare them to what the sensors are saying. It's a very effective, efficient way to diagnose a car like this. Now you might ask, how can this car have no fuel trims but it's got a calibration issue? Well, the only time I had this car lay down is when you first start to get in it and the turbo starts to come up. And sometimes it was just laying down and it felt like the turbo just wouldn't pull, but really the fuel mixture was lean. So how can this happen? And that's because under wide open throttle, we're probably, the program just doesn't allow it to have as much fuel trim under wide open. Many cars don't have a lot of trim under wide open throttle. They limit the trim under wide open. The second thing you've got against you is you got to have enough fire cycles to fuel trim authority. The car only laid down for a couple of seconds and then it came up and it pulled strong. It was going lean, but it only was lean for maybe 2 to 3 seconds, and then it got fine and it would start to pull. Well, I don't think there's enough time in those few seconds and enough fire cycles to really get trim authority on top of a position to where they probably don't give a lot of trim authority on this car. Lots of vehicles will limit the fuel trim under wide open conditions. We all know Toyotas do that. I don't work on a lot of Subarus, but I can see that this has a similar system. So you don't see high fuel trims even though we have a fuel problem. But really, we all need to equip our shop so we can be successful out here in these little battles. Because some of these little battles like this car can really, they can bloody you up. You know, we've got to win the battle so we can win the war. I'm in a war. Every day I go out, all I work on is really difficult cars. And even if I didn't, when I had my shop and I got regular cars, I had a 5-gas because I know how valuable it is. When you got really wild trim skews, how else do I know that trim is valid until I see what's coming out the tailpipe? If the tailpipe gases are correct, then it needed that trim addition. It's really important to have the right equipment when you're working on these modern cars. If you guys have the right equipment and a little bit of knowledge, you too will be successful troubleshooting these type of cars and problems in your base. Okay guys, we all work on these RAF sensors and oxygen sensors every day, but many of us don't understand the inner workings of how these sensors are actually in function. So what I want to do is I want to put up some training now that you can watch. So I'm going to give you an in-depth evaluation on how an oxygen sensor and how a RAF sensor are operating. These are just-in-time training videos, and these training videos are embedded in our scope. So if you would have had our scope and you would have had, you're not sure of how these sensors work or how a sensor works, you can go to just-in-time training and you can play a little video that's like these, and it will give you an in-depth understanding. So when you're looking at the waveforms on your scope, you'll have a better understanding of how you're going to test that circuit or that system. So here they are. First we're going to play the 4-wire, and then we're going to put the 6-wire RAF up. You have to watch the 4-wire before you can understand the RAF. So please watch both of these in sequence the way they're intended to be watched, and hopefully this helps.
Automotive Test Solutions, ATS, just-in-time training. ZR02 4-wire oxygen sensor. The 4-wire zirconium oxygen sensor is an oxygen concentration cell. An oxygen concentration cell, when heated, is a galvanic device that produces voltage based on oxygen content. The difference in oxygen content between the atmospheric inner cell and exhaust outer cell is converted into a potential, or voltage. This voltage can be used by a microprocessor to control the fuel delivery to the spark ignition internal combustion engine. The oxygen sensor is placed in the exhaust system where it can read the oxygen content within the exhaust stream. The microprocessor takes in data from the input sensors. This data is then equated to the base fuel delivery. The injection on time is then set, and the microprocessor opens the injector, allowing fuel to be injected into the engine. The air-fuel mixture is then drawn into the cylinder where it is ignited and burned. During the burn of the air-fuel mixture, a chemical reaction occurs that alters the oxygen and hydrocarbons. The oxygen combines with the carbon and hydrogen to form into CO, or carbon monoxide, CO2, or carbon dioxide, and H2O, water. If the air-fuel mixture is stoichiometric, or 14.7 pounds of air to 1 pound of fuel, a complete reaction can occur. This is due to the reactant's weight ratio being chemically correct. In a complete reaction, all of the original chemicals will react with one another, which will allow all of the original chemicals to change into different chemical compounds. In the engine, oxygen will react with hydrocarbons. In a complete reaction, there will no longer be oxygen or hydrocarbons, but these chemical compounds will be changed to CO, CO2, and H2O. In a lean air-fuel ratio, more air than fuel, an abundance of oxygen will be left at the end of the reaction. This is due to fewer hydrocarbons being available for the oxygen to react with, thus leaving extra oxygen after the ignition and burn of the fuel. In a rich air-fuel ratio, less air than fuel, very little oxygen will be left at the end of the reaction. This is due to more hydrocarbons being available for the oxygen to react with, thus leaving very little oxygen after the ignition and burn of the fuel. These chemicals are then pushed out of the cylinder into the exhaust system, where the zirconium dioxide oxygen sensor reads the amount of oxygen in the exhaust stream. The microprocessor uses the oxygen sensor to check its base fuel equation. If the base fuel equation needs to be altered, the injection on time will then be changed. This is referred to as a feedback system. In a feedback system, the microprocessor has the ability to check and alter the base fuel equation. The microprocessor can now target the correct air-fuel mixture. In most cases, this will be stoichiometric, 14.7 to 1. This air-fuel ratio will optimize the efficiency of the three-way catalytic converter for both oxidation and reduction of exhaust pollutants. A voltage reading varying between 0.1 volts and 0.8 volts produced from the zirconium oxide sensor is stoichiometric. If the air-fuel mixture has more air than fuel, or is lean, the voltage produced from the zirconium oxide sensor will be low, or less than 0.1 volt. If the air-fuel mixture has less air than fuel, or is rich, the voltage produced from the zirconium oxide sensor will be high, or greater than 0.8 volt. The 4-wire zirconium oxygen sensor is considered to be a wideband oxygen sensor. This sensor can accurately read mixtures from 11 to 1 in the rich and 17 to 1 in the lean. In order for this oxygen sensor to work, the sensor must be hotter than 575 degrees Fahrenheit. The hotter the oxygen sensor is, the more accurate it will read. The heater contained in the oxygen sensor will keep the sensor hotter than the exhaust gases. The heater will allow the zirconium dioxide to reach its operating temperature much faster. This allows the sensor to close loop in 15 to 20 seconds. This is why the 4-wire zirconium oxygen sensor with the heater element can be located away from the engine or exhaust manifold. In these locations, if the heater circuit fails, the sensor's temperature will fall, allowing the sensor's output to fall as well. Now let us examine how the zirconium oxygen sensor is made and how it works. The exhaust manifold holds the oxygen sensor in the exhaust stream. The graphite seals provide a seal between the exhaust stream and the atmosphere. These seals also provide an electrical contact between the platinum electrodes and the conductor. The atmospheric duct allows oxygen from the atmosphere to enter into the inner cell. This duct may be located in the sensor's housing or the sensor's wiring harness. If this duct becomes restricted from mud, oil, or debris, the sensor's calibration will shift. The ceramic heater heats the oxygen sensor above the exhaust gas temperature, which allows the sensor to respond to changing air-fuel mixtures more quickly. It also allows the sensor to read more accurately over a wider range. Depending on the ceramic heater's temperature, the amp draw will be about 1 amp. The inner cell holds the atmospheric oxygen until the difference in the oxygen partial pressure is great enough for the oxygen ions to migrate through the zirconium dioxide. The positive electrode is connected to the inner platinum electrode and will carry a positive charge. The negative electrode is connected to the outer platinum electrode and will carry a negative charge. The negative platinum electrode allows a catalytic reaction between the carbon, hydrogen, and oxygen. The zirconium dioxide with yttria stabilizer will only allow an oxygen ion to pass through it. All other atoms or molecules will be blocked from migrating through the zirconium oxide. If the zirconium dioxide is damaged or cracked, then the calibration of the sensor will shift. The positive platinum electrode allows a catalytic reaction to split the oxygen molecule into an oxygen ion. The protective magnesium spinel is an oxide of magnesium and aluminum that protects the negative platinum electrode. The protective outer cover with slots is designed to dampen and smooth the fluctuation of exhaust gases. The ground in the 4-wire zirconium oxygen sensor is an insulated ground that is wired directly to the microprocessor. With this design, there's fewer ground problems with the ground circuit. If there's any resistance in the ground circuit, the oxygen sensor signal voltage will rise. When the air-fuel mixture is lean, there is an abundance of oxygen at the outer cell. The oxygen in the inner cell is not attracted by the oxygen on the outer cell. In this condition, there's very little difference in the chemical balance or equilibrium of the oxygen between the inner cell and the outer cell. Since the oxygen partial pressure is almost equal, there's very little pull on the oxygen ions, so very few oxygen ions will migrate across the zirconium oxide. When the air-fuel mixture is rich, there is a lack of oxygen at the outer cell. The oxygen in the inner cell is attracted by the hydrogen and carbon monoxide on the outer cell. In this condition, there's a much greater difference in the chemical balance or equilibrium of the oxygen between the inner cell and the outer cell. This vast difference in the oxygen partial pressure increases the force on the oxygen ions so that a greater number of oxygen ions will migrate across the zirconium oxide. The oxygen sensor tries to maintain equilibrium between the inner cell and the outer cell. The Hc, Co, and H2 exert a force that pulls the oxygen ions across the zirconium dioxide. For the oxygen to migrate across the zirconium dioxide, the oxygen molecule is catalytically dissociated into oxygen atoms. As the oxygen molecules are split into single oxygen atoms, each freed oxygen atom takes on 2 electrons and becomes an oxygen ion. The oxygen ion is attracted by the CO and H2 on the outer cell of the zirconium dioxide sensor. The oxygen ion migrates across the zirconium oxide where it gives up the 2 extra electrons to the outer platinum plate. The oxygen ions then associate with each other to form diatomic oxygen molecules, or they react with CO and H2 to form CO2 and H2O. The outer platinum plate is now charged negatively, and the inner platinum plate is now charged positively. The potential difference between the plates is voltage. This voltage is created by the oxygen migration through the zirconium dioxide. The oxygen migration through the zirconium dioxide is created by the fuel molecules that collect on the outer cell. This zirconium dioxide sensor is much more than an oxygen concentration cell. It's actually a fuel cell operating as an oxidation reduction reaction cell. The microprocessor can use this information from the zirconium dioxide sensor to accurately control the air-fuel ratio in the internal combustion engine. To check the operation of the zirconium oxygen sensor, make sure the sensor is hot and the engine is at operating temperature. drive the system rich with propane, and drive the system lean by creating an air leak. Make sure the voltage output from the sensor exceeds 0.8 volts in the rich and drops below 0.1 volt in the lean. The time it takes to change states from lean to rich or rich to lean should occur in less than 125 milliseconds. To check the calibration of the zirconium oxygen sensor, an exhaust gas analyzer will be used. If the cell voltage is cycling from 0.1 to 0.8 volts and the gases do not show a lambda of 1, the sensor is out of calibration or the exhaust has false oxygen entering the exhaust system. Thank you for your support of ATS. This concludes your just-in-time training session. Contents are copyrighted property of Automotive Test Solutions, all rights reserved. Automotive Test Solutions, ATS, just-in-time training. 6-wire RAF sensor. Please watch the just-in-time training animation entitled ZRO2 Single-Wire Oxygen Sensor before proceeding. The 6-wire wide-range air-fuel ratio, or RAF sensor, is an amperometric oxygen pumping cell coupled with a potentiometric oxygen sensing cell. The amperometric, current-based, and potentiometric, voltage-based cells are made of zirconium dioxide with a yttria stabilizer. When two zirconium dioxide cells are used together, they can provide information to the microprocessor on a wide range of air-fuel ratios. The RAF sensor can detect an air-fuel mixture in the rich of approximately 11.5 to 1 and an air-fuel mixture in the lean of approximately 24 to 1. This sensor uses current flow across the pumping cell to detect the air-fuel ratio in the spark ignition internal combustion engine. The RAF sensor is placed in the exhaust system where it can read the exhaust gas stream. Now let us examine how the 6-wire RAF sensor is made and how it works. The 6-wire RAF sensor is constructed with a ceramic, layered, thick film construction that is referred to as a planar construction. The planar oxygen sensor heater element is layered into the sensor. This allows the temperature of the sensor to be maintained in a range of 1112 degrees Fahrenheit to 1652 degrees Fahrenheit with as little as 1 to 2 amps of current draw. With the RAF sensor's heater element being layered into the sensor, this sensor can obtain operational temperature in 10 to 20 seconds. This enables closed loop to occur quickly, allowing total fuel control in cold start conditions. Let us examine a cross-section of the RAF sensor. The exhaust gas intake is approximately 0.8 millimeters in diameter. The exhaust gases enter through this duct and diffuse into a very narrow diffusion gap between the zirconium pumping cell and the zirconium sensing cell. The 6-wire RAF sensor is comprised of two zirconium dioxide oxygen sensors, stacked one on top of the other. The zirconium dioxide cell on the exhaust side is an amperometric oxygen pump. An oxygen pump can pump oxygen ions from one side of the pumping cell to the other side of the pumping cell. The pumping cell must be above 1100 degrees Fahrenheit for the oxygen ions to properly move through the zirconium dioxide. The pumping cell functions by applying a potential or voltage to the platinum electrodes. If one electrode is negatively charged and the other electrode is positively charged, then the oxygen ions will be pulled across the zirconium dioxide. The oxygen molecule will be catalytically dissociated on the negative platinum electrode, becoming an oxygen ion. The oxygen ion will now be pulled across the zirconium dioxide to the positive platinum electrode, where the oxygen ions will then associate with each other to form diatomic oxygen molecules. If the potential across the cell is reversed, the oxygen ions will be pumped in the opposite direction. The second zirconium dioxide cell on the atmospheric side is a potentiometric sensing cell. This cell's operation is just like the basic zirconium dioxide oxygen sensor. When the air-fuel mixture is lean, there is an abundance of oxygen at the outer cell. The oxygen in the inner cell is not attracted by the oxygen on the outer cell. In this condition, there is very little difference in the chemical balance or equilibrium of the oxygen between the atmospheric inner cell and the exhaust outer cell. Since the oxygen partial pressure is almost equal, there's very little pull on the oxygen ions, so very few oxygen ions will migrate across the zirconium oxide. In this lean condition, the oxygen sensor will produce a low voltage of less than 0.1 volt. When the air-fuel mixture is rich, there's a lack of oxygen at the outer cell. The oxygen in the inner cell is attracted by the hydrogen and carbon monoxide on the outer cell. In this condition, there's a much greater difference in the chemical balance or equilibrium of the oxygen between the atmospheric inner cell and the exhaust outer cell. This vast difference in the oxygen partial pressure increases the force on the oxygen ions so that a greater number of oxygen ions will migrate across the zirconium oxide. In this rich condition, the oxygen sensor will produce a high voltage of greater than 0.8 volts. When the air-fuel ratio is stoichiometric between 0.1 volts and 0.8 volts, the oxygen sensor's voltage becomes very sensitive. The RAF sensor takes advantage of this rapid voltage change between lean and rich air-fuel ratios. The RAF sensor targets 0.45 volts. This voltage will change quickly if any change in the air-fuel is sensed. The RAF sensor tries to keep the sensing cell at 0.45 volts by using the oxygen pumping cell to move oxygen into and out of the diffusion chamber. The diffusion chamber is located right above the sensing electrode. The sensing cell is reading the exhaust gas content that is contained in the diffusion chamber. The RAF sensor controls the exhaust gases in the diffusion chamber by pumping oxygen into the diffusion chamber in the rich and pumping oxygen out of the diffusion chamber in the lean. By controlling the amount of oxygen in the diffusion chamber, the sensing cell can be maintained at approximately 0.45 volts. The air-fuel ratio can be accurately calculated by measuring the pumping current required to keep the sensing cell at 0.45 volts. One example of this is if 3 tanks are used with a pumping system to maintain the sensing tank at a given level. If the pumping system is disabled and more fluid is dumped into the exhaust tank, then the volume of all 3 tanks will increase, causing the levels in the tanks to rise. If less fluid is dumped into the exhaust tank, then the volume of all 3 tanks will decrease, causing the levels in the tanks to fall. If the pumping system is activated, it can maintain the sensing tank to a given level regardless of how much fluid is dumped into the exhaust tank. If less fluid enters the exhaust tank, the fluid level will drop. In order to keep the sensing tank level from dropping, the fluid from the exhaust tank will be pumped into the diffusion tank. This in turn will keep the sensing tank at a given level. The less fluid entering the exhaust tank, the more fluid will need to be pumped from the exhaust tank into the diffusion tank. By measuring the amount of fluid used to maintain the sensing tank's level, the amount of fluid entering the exhaust can be calculated. If more fluid enters the exhaust tank, the fluid level will rise. In order to keep the sensing tank level from rising, the fluid from the diffusion tank will be pumped into the exhaust tank. This in turn will keep the sensing tank at a given level. The more fluid entering the exhaust tank, the more fluid will need to be pumped from the diffusion tank into the exhaust tank. By measuring the amount of fluid used to maintain the sensing tank's level, the amount of fluid entering the exhaust can be calculated. By measuring the rotation of the pump, the gallons pumped into or out of the diffusion tank will be known. This will give the precise total amount of fluid entering the exhaust tank. This is similar to how the RAF sensor and its circuit work to calculate the air-fuel ratio of the internal combustion engine. In the rich, there's very little oxygen in the diffusion chamber. The sensing cell's voltage starts to rise above 0.45 volts. This voltage goes to a differential amplifier. The voltage sensed, VS, is fed to the negative leg of the differential amplifier. The differential amplifier's positive leg is connected to the voltage reference, or VR. This voltage is maintained at approximately 3 volts. This causes the differential amplifier to invert the voltage out, or VO, signal. The amplification of the voltage sensed, VS, is multiplied many times and is set by the type of differential amplifier. In the rich, the voltage sensed, VS, rises, causing the voltage out, VO, to drop. In turn, this lowers the voltage to the exhaust platinum pumping electrode below 2.55 volts. This electrode becomes more negative than the diffusion pumping electrode. Oxygen is now pumped from the exhaust into the diffusion chamber, thus maintaining the sensing cell at approximately 0.45 volts. In the lean, the voltage sensed, or VS, drops. This differential between voltage sensed, VS, and voltage reference, VR, causes the voltage out, VO, to rise. The differential amplifier raises the voltage to the exhaust platinum pumping electrode above 2.55 volts. The electrode becomes more positive than the diffusion pumping electrode. Oxygen is now pumped out of the diffusion chamber to the exhaust, thus maintaining the sensing cell at approximately 0.45 volts. The microprocessor uses a shunting resistor placed in the pump circuit between the differential amplifier output and the exhaust platinum pumping electrode. The voltage drop across the shunting resistor is proportional to the current flowing through the pumping circuit. During the production of the planar RAF sensor, the sintering process with green sheet thick film technology causes the diffusion chamber's size to change. The diffusion chamber will vary 10 to 50 microns in size. This size variation changes the gas rate determining diffusion. When close to stoichiometric, there's very low current flow, so the size variation of the diffusion chamber will have little influence. However, in the rich or in the lean, as current through the pumping circuit increases, the sensor's dispersion can be inaccurate by plus or minus 15%, thus changing the total pumping current. This is compensated for by adding a parallel circuit to the pumping circuit. This parallel circuit has one fixed resistor in the PCM and one adjustable resistor in the RAF sensor's connector. A parallel circuit leg is added to the pumping circuit to divide the pumping current between both circuits. Manufacturers use an adjustable resistor built into the RAF sensor's connector to alter the total pumping current. By adjusting this calibration resistor, the RAF sensor can be adjusted to read the air-fuel ratio accurately. The RAF sensor's connector has a precision resistor that is adjusted by the manufacturer and is called the calibration resistor. This calibration resistor can hold the dispersion to within plus or minus 1%. This calibration resistor can vary between 30 ohms and 300 ohms, depending on the diffusion chamber in each individual RAF sensor. The microprocessor measures the voltage drop across the shunting resistor, located in the pumping circuit, with an analog to digital converter. This voltage drop is equal to the air-fuel mixture in the engine. When connecting the oscilloscope to the RAF sensor, there are 6 possible connections: 2 to the heater circuit, 2 to the sensing cell, and 2 to the pumping cell. Of the 2 wires that connect to the heating circuit, one will have battery power and the other will be a controlled square wave being pulled to ground. This will control the temperature of the heating element. The heater circuit is very important on the sensor. If the heater circuit has any problem, the RAF sensor will not function properly. The heater circuit should draw 1 to 2 amps, depending on the heater element temperature and the battery voltage supplied. Of the 2 wires that connect to the sensing cell, one will carry a reference voltage that will be approximately 2.55 volts. This is a voltage that will raise the sensor's reference above ground voltage. The other sensing cell wire will produce 0.45 volts once the sensing cell is operational. The total sensing voltage will be 3 volts. The 2.55 volts from the reference plus the 0.45 volts produced from the sensing cell equals 3 volts. The sensing cell's voltage will change approximately 25 millivolts depending on the air-fuel ratio that's contained in the diffusion chamber. Some manufacturers will vary the sensing cell's reference voltage. This voltage may range from 2.4 to 2.7 volts. Of the two wires that connect to the pumping cell, one wire will connect to the shunting resistor circuit, the other wire will connect to the calibration resistor circuit. At low pumping current levels, the two pumping voltages will follow each other very closely. As soon as the pumping current is increased, the two pumping voltages will vary from one another. This is due to the different resistance values of the two circuits. If the engine is lean, the pumping voltage will be greater than the 2.55 reference voltage at the pumping cell. The greater the voltage, the leaner the air-fuel ratio. If the engine is rich, the pumping voltage will be less than the 2.55 reference voltage at the pumping cell. The lower the voltage, the richer the air-fuel ratio. If the air-fuel ratio is stoichiometric, or 14.7 to 1, the pumping cell voltage will be crossing the 2.55 reference voltage. This will be a cyclic waveform of rich, lean, rich at a frequency of 1 to 2 Hertz. Be aware that this voltage is reversed from a conventional zirconium dioxide oxygen sensor. If the voltage is high, above 2.55 volts, the system is lean. And if the voltage is low, below 2.55 volts, the system is rich. The sensing cell voltage should be very stable at approximately 3 volts, and the pumping cell voltage should be actively crossing the 2.55 voltage reference. This shows that the sensor is working correctly. To check the operation of the RAF sensor, drive the system rich with propane and drive the system lean by creating an air leak. Make sure the pumping cell voltage in the rich drops below 1.85 volts. Make sure the pumping cell voltage in the lean exceeds 3.5 volts. To check the calibration of the RAF sensor, an exhaust gas analyzer will be used. If the pumping cell voltage is cycling across the 2.55 volt reference and the gases do not show a lambda of 1, the sensor is out of calibration or the exhaust has false oxygen entering the exhaust system. Thank you for your support of ATS. This concludes your just-in-time training session. Contents are copyrighted property of Automotive Test Solutions, all rights reserved.